Hello, welcome to lecture 18 of solitons. In the last 3 lectures of the term, we will study the so-called Hirota method. That's chapter 6, which will be based on section 5.3 of the book by Drazen and Johnson. The Hirota method is an alternative to the Backlund transform. As a way to generate multi-soliton solutions. And it is sometimes available when the Backlund transform is not. So it's useful to study that method as well. It was devised by Hirota in 1971 to find multi-solitons, let's say, and soliton solutions of the KdV equation. It was then understood that this method applies to a much more general class of equations, but in this chapter, we'll follow Hirota and apply it to the KdV equation. As you will see later today and next time, the Hirota method can be quite technical. So let me start with some motivation. So we're interested in KdV equation, ut plus 6 ux plus uxxx equal to 0. And what we'll do is to substitute for the field, the KdV field u, wx. So we write the KdV field as a partial derivative with respect to x of another field w. So when we make this substitution in the KdV equation, we get the following equation for w, wxt plus 6 wx wxx plus wxxxx for derivatives equal to 0. And now we can integrate this equation with respect to x to get wt plus 3wx squared plus wxxx equal to an integration constant, which is constant with respect to x, but in general will be a function of t. I'll call that function g of t. So it's annoying to have this function of t in the right-hand side, but luckily we can get rid of it with no loss of generality. So the integration constant which I write in quotes because it's only constant with respect to x, but not with respect to t, g of t can be absorbed by a redefinition of w that doesn't change the KdV field u, which is x derivative of w. So concretely, we can write the old w, which appears in the question upstairs, as a new w plus a time derivative of g. So that when we calculate the derivative with respect to t of the old w, we get an extra term. We get the derivative of the new w plus an extra term, which is precisely equal to gt, and that cancels the right-hand side. So if we use the new w, and for simplicity, we drop the subscript new, we get the following equation for the new w, which is wt plus 3 wx squared plus wxxx equal to 0, a nice homogeneous equation. All right, so instead of the KdV equation for u, we have equation 6.2 for w. But at this point, you might ask, why at all did we make the substitution 6.1, where u was equal to wx? So let's try to answer that question next. So why do we make the substitution 6.1, which was u equal wx? Well, recall that the one soliton solution of KdV took the following form. U was equal to 2 mu squared hyperbolic secant squared of mu times x minus x naught minus 4 mu squared t, where I introduced mu, which is the square root of v, where v is the velocity, over 2, and therefore is non-negative to avoid writing square roots everywhere. And now we observe that we can rewrite this one soliton solution of KdV as u equal to wx, which is a substitution that we just considered, with w equal to 2 mu hyperbolic tangent of mu times x minus x naught minus 4 mu squared t. That's because the derivative of the hyperbolic tangent is the hyperbolic secant squared. But in fact, we can integrate the right-hand side of 6.5 once more. Using the fact that the hyperbolic tangent of y is equal to the derivative with respect to y of the logarithm of the hyperbolic cosine of y. So when we differentiate the log of cos y, we get 1 over cos y times the derivative of cos y, which is sinh y, and that reproduces the hyperbolic tangent of y. And therefore, the one soliton solution of KdV 6.3 can be written as a second partial x derivative. So u is equal to 2 times the second derivative with respect to x of the logarithm of the hyperbolic cosine of mu times x minus x naught minus 4 mu squared t. This is already nice and quite useful, but we can simplify 6.6 further, and to do that, let capital X be x minus x naught minus 4 mu squared t, the function of x and t, which appears in the argument of the hyperbolic cosine. So then we can write the one soliton solution as twice the second derivative with respect to capital X, which is the same as the second derivative with respect to small x, if we change variables from small x and t to capital X and t, of the logarithm of the hyperbolic cosine of mu times x, and I'll write that as e to the minus mu x, which multiplies 1 plus e to the 2 mu capital X, all divided by 2. So why did I factor the numerator of the hyperbolic cosine e to the mu x plus e to the minus mu x in this way? Well, the reason is that the logarithm of the product is the sum of logarithms, so we can rewrite this as twice the second derivative with respect to capital X of the logarithm of e to the minus mu x, which is nothing but minus mu x, plus the logarithm of 1/2, which is minus logarithm of 2, plus the logarithm of 1 plus e to the 2 mu capital X. And now the first two terms that we take the derivatives of are linear in x, or constant in x, so they disappear when we calculate the second derivative. And so we simply get that u is equal to twice the second derivative with respect to this new variable x of the logarithm of 1 plus e to the 2 mu capital X, which we can rewrite in terms of the original coordinates, small x and t, as follows. U of x and t is twice the second derivative with respect to x of the logarithm of 1 plus exponential of 2 mu times x minus x naught minus 4 mu squared t. And this is the form of the one soliton solution of KdV that we will use in the following. Let's recap before we proceed. So what we did was to substitute u equal to wx, equation 6.1, in the KdV equation. And then we found an equation for w that after integrating once with respect to x and redefining w to get rid of an integration constant, became equation 6.2. But then we noticed that if we looked at the one soliton solution of the KdV equation, it can indeed conveniently be written as a partial derivative with respect to x of a function. But in fact, we can do more. And as you can see in equation 6.8 that we just derived, we can write one soliton solution of the KdV equation as the second partial x derivative of a function, which in this case is this log of 1 plus the exponential. This observation naturally leads us to section 6.2, where eventually we will write the KdV equation in a so-called bilinear form. We'll get to that bilinear form of KdV towards the end of the lecture, but first let's try to rewrite the KdV equation in a quadratic form. So inspired by equation 6.8 for the one soliton solution of KdV, let's substitute W equal to twice the partial derivative with respect to x of the logarithm of a new field f, which is equal to 2fx over f. Or equivalently, in terms of u, that means that u is twice the partial derivative with respect to x of log f. In equation 6.2. So then we'll need to calculate a few derivatives of this w. So we need partial derivative of w with respect to t. And let me divide that by 2 to simplify the formula on the right-hand side. So I need to differentiate with respect to time the previous expression for w. So I get 1 over f squared times the t derivative of the numerator. So that's fxt times the denominator, which is f, minus numerator times the time derivative of the denominator, which gives me fx ft. And similarly, a half wx will be equal to fxx f minus fx squared over f all squared. So then we can we need the third derivative of w with respect to x in 6.2. So we'll have to calculate a half wxx, but I'll let you do that as part of exercise 35. And when you differentiate once more to get 1/2 wxxx, and that's again part of exercise 35, you will get the following expression: fxxx over f minus 4 fxxx fx over f squared minus 3 fxx squared over f squared plus 12 fxx fx squared over f cubed minus 6 fx to the 4th over f to the 4th power. And when you do that, then equation 6.2 for w, which I remind is this equation here, becomes the following equation for f. So we'll have fxt over f minus fx ft over f squared plus 3 fxx squared over f squared minus 4 fxxx fx over f squared plus fxxxx over f equal to 0. So this is the equation that we find for f. And in exercise 35, you will have to work out the details of this calculation and confirm this final equation for f. If we multiply by f squared throughout, we get the following equation: fxt minus fx plus 3 fxx squared minus 4 fxxx plus f times fxxxx equal to 0. This equation is quadratic in f and is known as the quadratic form of the KdV equation. When you do exercise 35 and you derive this quadratic form of the KdV equation 6.11, starting from the equation for W that we wrote earlier, you will notice that some cancellations take place along the way. But at first sight, it might not look like this quadratic form of the KdV equation is much progress compared to the initial equation 6.2 for W, which only involved 3 terms. However, the advantage of 6.11 is that it's quadratic in f. And its derivatives. And as a result of this, it can be rewritten in a neat way. So how can we rewrite this quadratic form of the KdV equation in a neat way? Well, the hint is given by the fact that here the first 2 terms resemble very much a second partial derivative. So if we consider partial derivative with respect to x and partial derivative with respect to t of 1/2 f squared, which is the same as partial derivative with respect to x of ft. This is given by fxt plus fx ft. So this is almost like the first 2 terms in 6.11. If it weren't for the relative sign, which is plus when we take the second mixed derivative of 1/2 f squared, and minus in the first 2 terms in 6.11. This takes us to section 6.2.2, where we encounter Hirota's bilinear operator. So I'll define Hirota's bilinear operators in a second, but let me first tell you what they are. These are bilinear differential operators which I'll call D now. So we'll see there are many such differential operators. We'll be interested in a particular one later, but let's construct a class of differential operators, which I'll schematically call D. And these differential operators D map a pair of functions f comma g into a single function. The f comma g. Note that this is unlike the usual linear differential operators that you're familiar with. Like, for instance, the nth derivative with respect to x, which maps a single function f into another single function, which is a nth partial derivative of f with respect to x. So instead, a bilinear differential operator maps a pair of functions into a single function. So let's say that we have the operator d, and for definiteness, let's take our function to be c infinity, so infinitely differentiable. So d takes a pair of functions in c infinity times c infinity. I'll call the two functions f and g, and maps them into another function, which will be, again, c infinity, and we call that d of f comma g. So, and this is a function of x, and for us, in fact, will be functions of x and t, since we're always interested in functions of two variables. All right, how do we define these bilinear differential operators? Well, let's define an infinite class of those, and then we'll use a particular linear combination. So let's define for all integers m and n, which are non-negative, the following bilinear differential operator, which I call capital D t to the m, capital D x to the n, which acts on the pair of function f and g. So I remind you, this is a new function, so it will be a function of x and t. And this is defined as follows. So for capital dt to the m, we take a partial derivative with respect to t minus partial derivative with respect to t prime, m times. And then for dx to the n, we get partial derivative with respect to x minus partial derivative with respect to x prime, n times of now a product of two functions, f, which is a function of x and t, and g, which is a function of x prime t prime. Okay, I need some space, so let me move this to the left. So what we have so far on the right-hand side is a linear differential operator in the variables tx and t prime x prime, which acts on the product of two functions f of x and t and g of x prime t prime. But the result of this bilinear differential operator dt to the m, dx to the n, applied on the pair of functions f and g, must be a function of x and t. And we achieve that by setting x prime equal to x and t prime equal to t after we have calculated these derivatives. To get a feel for this definition of bilinear differential operators, let's look at a few examples. So we'll start by looking at dt acting on the pair of functions f and g. And this, I remind you, is a single function of x and t. So what we have to do is to apply partial derivative with respect to t and then subtract partial derivative with respect to t prime of f of x comma t times g of x prime t prime. And once we've done that, we set x prime equal to x and t prime equal to t. So let's do it slowly. So when we act with the first time derivative with respect to t, we get ft of x t times g of x prime t prime. And then we have minus time derivative with respect to t prime. So that gives f of xt times g t prime of x prime t prime. And then we set the prime coordinates to be equal to the unprimed coordinates. And so we get ft of x comma t times g of xt minus f of xt times gt of xt. Or in short, dt of f comma g is equal to ft g minus f gt. This is equation 6.13. Which in particular implies, if we take g to be equal to f, that dt of f comma f is equal to 0. Next, let's look at dt dx acting on the pair of functions f comma g. At this point, I'll stop writing the dependence on the coordinates x and t when there is no doubt about that. So here we have partial with respect to t minus partial with respect to t prime, and partial with respect to x minus partial with respect to x prime of, again, f of xt, g of x prime t prime. And then we set primed and unprimed coordinates to be equal. I'll also stop writing that in detail. I'll just write a vertical bar. So let's first do the x and x prime derivatives. So we still get the partial derivative with respect to t and t prime in front. And then what we have is fx of xt times g of x prime t prime minus f of xt g x prime of x prime t prime. So important point to notice is that unprimed derivatives act only on f. So we get fxt g minus ft gx, and then the prime derivative only acts on g. So we get minus fx gt minus f gxt, and we get a plus sign for the last term because of the two minus signs. That's equation 6.14. And in particular, if we take g to be equal to f, we get that dt dx acting on the pair of functions f comma f is equal to twice fxt from the first and the last term minus ftfx from the second and third term. Which is precisely, up to the overall factor of 2, what appeared in the first two terms in the quadratic form of the KdV equation 6.11. I remind you, equation 6.11 is this equation here. And we've reproduced the first two terms, which involves derivatives with respect to x and t. So there are three more terms which always involve a total of 4 x derivatives. So that suggests that we look at the Hirota bilinear differential operator, capital Dx to the 4th power. But before we look at that, let's consider a final example, which is dx squared acting on the pair of functions f comma g. And we don't need to repeat the calculation. What we can do is simply to replace subscript t for derivative with respect to time in 6.14 with subscript x for derivative with respect to x. And so we find that dx squared acting on f comma g is equal to fxx minus 2 fxgx plus fgxx. This is a question 6.16. So when we take g to be equal to f, we get 2 times fxx minus fx squared. And let me make an observation here, which is that dx squared acting on the pair of functions f comma f is non-vanishing, even though dx acting on f comma f is equal to 0. Indeed, dx squared acting on f comma f is not dx acting on dx, which acts on f comma f. In fact, the right-hand side here is meaningless because dx acting on f comma f is a single function, but the outer Hirota capital Dx needs to act on a pair of functions. And the reason for this peculiar properties is that in the definition of these bilinear differential operators, we have ordinary differential operators with respect to x and t, x prime and t prime. So those compose in the natural way, but at the end we set unprimed variables to be equal to the primed variables. And once we've done that, we can no longer take derivatives with respect to the two sets of variables independently. All right, then as I've hinted, we might be interested in calculating dx to the 4th power acting on pair of functions f comma g. This is left as an exercise, which is exercise 36. We might look at it in the last problems class next week. And when you do that, the result that you find is that this is fxxx times g minus 4 fxxx times gx plus 6 fxx gxx minus 4 fx gxxx plus f gxxxx. Now observe that what we found is essentially the same result that you get when you calculate the 4th ordinary x derivative of the product f times g. But now we have alternating signs. So we'll explore this further in the problems class. And then let me specialize, as usual, G to be equal to F. So we have dx4 acting on F, comma F. I can now group the terms in 6.17 in pairs, and I get 2 times F times Fxx from the first and last term, minus 4Fxx from the second and fourth term, and plus 3Fxx squared from the middle term. And now it's a miracle when we look at these 3 terms on the right-hand side of 6.18, we can see that these are precisely the last 3 terms that appeared in the KdV equation written in its quadratic form, 6.11. So we reproduced the first 2 terms in the equation, 6.11, by taking dx dt, the Hirota operator. And now we reproduce the last 3 equations by taking dx to the 4th power. So let me write it down. Here's the miracle. The KdV equation in its quadratic form (6.11) can be recast as dt dx plus dx to the 4th acting on f comma f is equal to 0. This is the so-called bilinear form of the KdV equation. This is the final result for today, but let me make one last comment. And the comment is that here we have the Hirota operator dt dx plus dx to the 4th, which we can formally factorize as dt plus dx cubed times dx. I say formally because the factorization only works when you use both primed and unprimed coordinates before setting them equal. But this is what I mean here. And the comment is that it's not an accident that these derivatives, these Hirota derivatives appear. The reason is that, well, first let's look at dt plus dx cubed. Well, if we replace the Hirota derivatives by partial derivatives, the partial derivative with respect to t plus the partial derivative with respect to x 3 times is nothing but the differential operator which appears in the linearized KdV equation. So if we take the KdV equation for u and we linearize it, we see that this operator. And so since u was equal to partial derivative of w with respect to x, then partial derivative with respect to t plus t partial with respect to x 3 times acting on dx is a differential operator which appears in the linearized equation for w, at least before integration. And that's really the reason why the Hirota operator dt dx plus dx to the 4th appears in the bilinear form above. That's all for this week. Next week, we'll use the bilinear form of the KdV equation to derive solutions of the KdV equation, which involve several solitons. And finally, we will conclude the term by studying their asymptotics. Have a safe trip home if you're going back, and see you next week.